right, let's get started. So, welcome everyone on this beautiful day in Malmö. I am Gabor Szarnyas and I'm here to talk to you about DuckDB. Who here has heard about DuckDB before? Okay, so you're an advanced audience. That's great. So let's get started. A few sentences about me. So I spent a long time in academia doing a PhD and a postdoc, mostly working on software engineering and database problems, with an emphasis on benchmarking and graph processing. I still like those topics, as you will see from the presentation, but now I am at DuckDB Labs, and I'm developer relationship advocate for the DuckDB database. DuckDB Labs is a small startup of about 18 people based in Amsterdam, and we developed the DuckDB system. To set the context for this talk, I would like to quote a tweet that was put out last week from DHH, David Heinemeier Hansson, who was born in Copenhagen, just across the strait. And here's what he had to say. He said that the fact that mainstream developer laptops now ship with 16-core 3nm CPUs is one of those the premise changed fundamentals. And he argues that it's time to reconsider some fundamentals of where things run, how and when. And what he likely had in mind when he was writing this was Apple's announcement of the new MacBook Pro lineup. If you buy the most expensive model, you will have the M3 Max CPU, which has 16 cores, comes with a lot of memory and a very fast SSD. And even the more affordable base model comes with an 8-core CPU and also a very fast disk. In fact, any laptop you buy these days is pretty amazing because they have lots of CPU cores and a fast memory. Then this prompts us to define DuckDB in the context of this. I would say DuckDB is an analytical database system that is built for this new era where the end user devices, laptops, tablets, and smartphones are very powerful. So DuckDB is an analytical database. It's built to be portable and fast from the ground up. It's been in development for the last 5 years. It's written entirely in C++11, and it's free open source under the MIT license. But how does it actually work, and how does it actually exploit the fact that we have all this modern hardware on our desk at our disposal? Well, we had to rethink the fundamentals, as DHH suggested, and this starts with the deployment model. Traditionally, it was a given that if you wanted to do analytical data processing, you had to have something called a client-server setup. So you had your laptop on the left. This is a client application written in Python. But you had a big, beefy machine, a database server running either on premises or in the cloud with lots of cores, lots of memory, and fast disk that did the actual number crunching for you. And this setup has a few problems. First, that big machine is going to be expensive. Likely, the license for the database software is also going to be expensive, and then you have to configure it, operate it, which incurs further costs. On the client side, you always have to fiddle a bit with the connection string, set up the authentication, and even once you have done all that, you have this tiny narrow straw in the middle, the client protocol. This is something that you have to push through the internet, and you have to serialize and deserialize your queries and data all the time, which is a major bottleneck in performance. So a natural idea would be to use these amazing laptops and bring the database server on the laptop. Unfortunately, this is not that easy. Database servers are big, unwieldy pieces of software. They are typically written with Linux in mind. So if you want to run it on macOS or Windows, you likely run it in a container. You need to still adjust some configuration files, play with ports, and the client protocol will still be a major bottleneck. So this is a very impractical setup, and in the last decade, I have only seen very few people to actually do so. It works, but it doesn't bring you that many benefits. But it gives us a good basis to explain what DuckDB does, because what DuckDB does is that it takes this idea even further. It says, if your database is on your laptop, why not just move it inside the client application and turn it into an in-process database? And you can immediately see the benefits. We have no configuration required, there is no authentication, the client protocol is gone, and the script is as simple as it can get. You import DuckDB, and then you can start firing your queries right away. Of course, this being a database, some persistence layer would be nice. and this is available. You can say, I want to connect to a .db file, and then you can run your queries against that DB file. You have a single file that contains all your tables. But at this point, you may be thinking, so you folks have invented a relational database system that runs in process, speaks SQL, and runs against a single file. That sounds familiar. Do you know of any other systems that does that? It is SQLite. SQLite is the most popular database system and arguably one of the most widely deployed pieces of software on the planet, with roughly 1 trillion deployments. In every major browser and every major smartphone, you will have multiple SQLite instances. But DuckDB is different. SQLite targets a transactional workload where you have lots of small reads and lots of small writes, never touching too much of the data. So if you map out database systems along these two axes, in-process versus client-server on the vertical axis and transactional workloads versus analytical workloads on the horizontal, you can immediately see the difference. There are many systems tackling the other categories, and you have great client-server analytical databases like Snowflake and Vertica, but DuckDB is quite unique in its category of being in-process and analytical. So we created this category for DuckDB, that's all great, but we promised that DuckDB is portable and fast, so let's see how that plays out in practice. Well, I claim that you can get started with DuckDB in less than 15 seconds on most popular platforms, and this includes typing the commands required to install DuckDB, downloading the packages from over the internet, and then launching DuckDB itself. I have two examples. On the left, we have macOS and the Python package. DuckDB is available from pip, so you can say pip install DuckDB. It will fetch the package in about a second, then you can start Python, import DuckDB, and start running your SQL queries right away. And the whole process just takes 12 seconds. It's a similar feeling in Windows. You can use install.packages in RStudio. It will grab it from CRAN. It's a small 8 megabyte package, and library DuckDB imports it without any hassle. And if you have ever installed one of those legacy relational database management systems, you know that this is very far from that experience. If you install traditional systems, your working hours will be probably in double-digit numbers by the time you finish all the configurations. So having this done this quickly is quite difficult. And this doesn't stop at Python and R. We have packages for Julia, Node, Java, Rust, for all major platforms. And these are binaries, so you don't have to compile DuckDB basically anywhere. Why is this so fast? Well, one of the philosophical bases of DuckDB is that it has 0 external dependencies, meaning that we don't depend on any binary package, DLL, or shared object that may lay around in your file system. Of course, we didn't reinvent things like regular expression matching or ZSTD compression. We took those pieces of code and we vendored them in the code base, which gives us a nice pure C++ code base that is portable to anywhere where you have a C++11 compiler available, which is pretty much anywhere where you have general purpose computing these days. This also allows us to have these small binary packages, which in turn help with the installation speed. This scalability, this portability is so extreme that you can take DuckDB and run it in your browser, so you can compile it against WebAssembly, and you will get a WebAssembly package that runs in your browser without talking to any server or any remote endpoint. This even runs on iOS, so this is a very nice way of having a SQL engine running within your browser. Okay, so DuckDB is fast to install, but is it actually fast in terms of processing? Well, for this, I reached back to my academic research and I grabbed something called the LDBC Social Network Benchmark dataset. And I used this dataset to demonstrate the loading performance of DuckDB. All of these experiments were run on this very laptop where I'm presenting from. And I made 3 different scale factors to demonstrate different use cases. The smallest one, 3.4 gigabytes, is something that you can load in just 3 seconds, basically in interactive time. The medium one, which is 35 gigabytes, is something you can load in less than half a minute. And even the largest one, which required me to clean up some disk space on my laptop to fit, that fits within less than 5 minutes. So if you add up the numbers, you will see that this laptop is capable of reading those CSV files from its disk, parsing them, and then writing them back to a compressed DuckDB format at more than 1.2 gigabytes per second, which is pretty amazing. And once you are done with the loading, you have these nice compressed representation. You can throw the original CSV files away and continue your queries and run your analytics on that. So let's do a demo on the middle dataset size, the 35 gigabyte dataset size. I have a browser running with Jupyter Lab. DuckDB also runs in Jupyter through its Python API. And as you can see, there is a few lines to initialize it. And I also set up the percentile SQL, which is this magic string that allows you to run SQL queries directly in Jupyter. So this is done all very quickly. And then I will load the data. Remember, I promised this will be a bit quicker than half a minute. So let's start this loading process. And in the meantime, I will show you around in the data. So we have this partitioned CSV dataset. And you can see that it's not actually a CSV. It's not comma separated, but it's pipe separated. So we have to tell Jupyter that it's pipe separated. But once we have done that, we can see that it's a very typical data set. It has a timestamp called creation date. It has an ID. It has some information on where the comment was created. It has the comment in the social network, its length, its creator, location, etc. OK, so I think the loading has finished by now. Let's go back to the demo. And indeed, it took 26 seconds to load 423 million rows. So the loading happens at more than 50 million rows per second. But hang on a second, we did not specify any types or even the delimiter. We just said create the table comment from the CSV as a command directory. So what's going on? Well, DuckDB has something called a CSV sniffer. And the CSV sniffer takes a sample of the loaded CSV files and tries to figure out your delimiters, your quote, and your data types. So if we say describe this comment table that we have just loaded, you can see that DuckDB has correctly identified all the column types and the column names, and of course the delimiter that separated these. So this is very neat. And if we start querying the dataset, we can see the same data with some truly high quality comments in the dataset that are part of it. We can see their length, and we can see that there are also some more long form posts in this network. OK, so let's do some number crunching. A natural question based on the data would be the average length of the comments. We can formulate it in SQL very quickly. We just want to count the rows and get the average length of the comments and return it. We can run it, and this takes less than 60 milliseconds for 185 million rows. If you extrapolate those numbers, you will get 3 billion rows per second in terms of aggregation performance, and DuckDB gives us an answer of 33.26. Let's do a more complex aggregation that has a group by. Maybe we want to take the creation date of the comments, extract the month, and then count the number of comments for each month. This is a group by aggregation, and this is again done very quickly in around 200 milliseconds. But now I saved it into something called a res. This is a Python result set, so we can not only return it as a data frame from Jupyter, but we can go to Python World and use all the available plotting libraries that are there to plot various data frames. So if we plot this, we get this nice looking plot that actually tells us something about the data. The number of comments have been steadily increasing until November, where they quickly dropped. Maybe there was a stop in data collection and the comments were only collected until the middle of November. So aggregation is definitely fast, but what about joins? Joins are the culprit of many slow relational database management systems, but they are extremely important. Joins are there to take multiple tables and construct tables from them where we can connect different entities and find connections between them. Let's take a look at the place table. The place table is very simple. It encodes name of countries and later continents based on a numerical ID. So we have something called location country ID in the data set where the post was supposed to be created. So let's do a ranking of the countries based on the number of comments. This requires a join and followed by a group by aggregation. And again, DuckDB makes quick work of it. It's just 350 milliseconds. And the result is not that surprising. It's countries with a large population that contribute most to the social network. All right, you may have noticed that we are in the pivot room, so it's time to do some pivoting. Pivoting is, of course, very important in data science. We use pivoting to turn long-form tables to white tables that look more like Excel sheets in a way. And they are really important and widely popular in data science. So let's create a long table first that has the number of distinct authors per month per continent. This is, again, a pretty heavy query. It has 2 joins, it has some extraction from a date, and it has a count distinct aggregation. And sure enough, it takes 1.6 seconds to run, and then we get this very long form table with more than 100 lines that the system actually had to cut after 10 lines. And now we can do the pivot. And the great thing about pivot is just how elegant it is. You say, pivot this table on the continent and put the sum of authors in the cells. And this is done instantly in 10 milliseconds, and we get the pivoted table that looks like an Excel sheet that you could play around with. And again, this is something that we can visualize very quickly. If you have Seaborn installed, then you can turn it into a heat map with a few lines. And you can see that we have the time passing along the y-axis to the bottom, and we have the continents. And this also tells us the relative distribution, the amount of distinct authors between the continents. All right, so we have saved this into something called df, which is a Pandas data frame. And this gives me an opportunity to demonstrate something interesting. So we acknowledge that SQL is great, but many users are not really familiar with SQL. They are much more comfortable in Pandas, and they can formulate their problems much easier in terms of Pandas' API. And this is totally all right in DuckDB. So if you want to manipulate the Pandas data frame with Pandas, you can do so by running this. We turn the month into quarters, and we create an average aggregate. So we now do number of distinct authors averaged over 3 months per quarter per continent. And then we get this table. But returning to DuckDB is actually very easy, because you can say something, select star from quarterly average to just get this row where the quarter is the 3rd quarter. And DuckDB does this very nicely. So what's going on here? Well, DuckDB has something called a replacement scan, which means that if it doesn't find this quarterly average in its catalog, it will look around in the environment, namely it's the host Python process, and it will find that there is a quarterly average variable that's a Python data frame, and it will read that without any copying. It's a 0 copy access on that, and it will run the queries on that. So you can very easily move in and out of Pandas land, run some queries in DuckDB, and run some queries in Pandas, all quite seamlessly. And finally, we have something called unpivot, because maybe long tables are not that bad after all. And we specify a very elegant construct here, which is, let's unpivot this table, but we don't want to spell out Africa, Asia, Australia, and so on. We just want to say unpivot it on all the columns except quarter. And we can do this on columns, asterisk, exclude quarter, and it will turn it back into the original long shape, this time with quarters as the initial column. So this is the demo of DuckDB. I hope it's something that convinces you that DuckDB is very fast. But what makes DuckDB actually fast in the background? Let's take a look at the internals. So it all starts at the storage, of course. Relational systems in general have 2 sorts of storage. Transactional systems use something called row-based storage. This is great because you can take all the attributes in a row and they are stored together in a disk. So I color-coded this table to represent how the data is stored row-wise. And if you only want to grab the 2nd row, then you just grab the green cells and you don't have to touch any of the other cells. But this is not necessarily great for analytics. When we often say, let's aggregate on time and then just do something with the length of the column. And in this case, it's much nicer if we have a columnar layout where the data is stored column-wise. This has quite significant trade-offs. The positive is that we have nicer access patterns, and we can have very good compression along these data types because we have the same data type in a single column stored sequentially. But updates are more difficult than in a row-based setup. And of course, the storage has a profound effect on execution. So in a row-based system, the systems typically do tuple at a time execution, meaning that the system gets a tuple, processes it, gets the next one, and the next one, and so on. And this is great because it saves on memory. A single tuple cannot be that big, so you basically never run out of memory, but you have to read all of the items in a single tuple, and you have to do a lot of context switches between each tuple. So it's not great for analytics. What's better is column at a time processing for analytics. And here, we can get an entire column and then get the other column, pull them into memory, and then do the processing on them. Now, this has very nice properties in terms of speed, but the problem is that we can have tens of billions of rows, and fitting a column with that many items is just not doable. So you will run out of memory and crash. So DuckDB uses a third approach, which is called the vectorized data model, where we use a columnar model, but get chunks of tuples out of it. And these chunks are usually 2048 items. So here we get one chunk of time and one chunk of length, followed by another chunk of time and another chunk of length. And this will give us the best of both worlds. So we will not run out of memory, but we will get the benefits of running bulkier operations. Let's see how this works in practice. So I created this table with 8 rows on the left. It consists of actually 2 row groups, the first 4 rows and the second 4 rows. And what DuckDB does is that it parallelizes the processing along these row groups. So the first goes to thread 1, and the second goes to thread 2. So these threads can then work independently, and they can take the vectors, and they can put it in the CPU. And the vectors, remember, are quite small, so ideally, they fit into the CPU's L1 cache, meaning that the processing on them is very quickly, and then we can go to the next pair of vectors and put them in the L1 cache. Because this is all in cache, which is roughly 32 to 128 kilobytes in size on modern computers, we have excellent locality. We don't have to do random accesses in the memory. Moreover, because they are in the cache, we can do something called SIMD vectorization. SIMD stands for single instruction, multiple data. And this means that we can do one CPU cycle and process multiple data with the same operation. For example, Intel has something called AVX 512, and this allows to add together 8 64-bit integers with a single CPU cycle. And this is, of course, hard to program manually, but modern compilers for the last decade or so do auto-vectorization. So if your code is written in a way that it uses these small vectors and it uses tight loops, and the compiler can deduce that this is a good opportunity to vectorize, it will do this auto-vectorization for you. And this is great because you can get something like a modern Intel Xeon CPU. It will have 52 cores. It will have AVX 512. So every single CPU cycle, it will do more than 400 addition potentially, not to mention other optimizations like pipelining in the CPU. So this is very friendly towards modern hardware architecture, and this is the secret sauce that allows DuckDB to be as fast as it is. Indexing-wise, it's an interesting question because I have been taught in my undergraduate database course that you always have to create an index for your database to be fast. And this is true. We don't want full table scans. Those would be, in general, pretty horrible. But DuckDB has a really elegant and simple method to get 99% of the benefits of having an index. And this is called a zone map. A zone map is a min-max index that is defined for every row group, and it defines the minimum value and the maximum value for all of the columns. So here on the left, we see that the minimum time and the maximum time for the first row group is the 7th of November and 8th of November. And for the second is the 8th and the 12th. And if we want to query for something like today, 9th of November, we can immediately just take a look at the min-max indexes and go to the second row group. There is no need to actually go to the other row groups. This is, of course, aided by the fact that the data is often sorted according to the timestamp. But this idea also works in many other cases. You can define it for something like the length, and then if someone asks what is the minimum length, then it's very simple to answer that. You just go look at the min-max indexes, conclude that it's 8, and return the result very quickly. Of course, on occasion, you would want secondary indexes, and DuckDB also supports that. You can define them implicitly if you create a primary key or a foreign key or a unique constraint, and you can also define them explicitly. But they come with serious trade-offs. Of course, they will speed up the high selectivity lookups when you're querying for less than 0.1% of your data, but they have a severe negative impact for bulk loading and updates. So as a rule of thumb, is that most of the time indexes are not needed, and if they are, create them after you have loaded the data. One nifty trick that DuckDB has is larger than memory execution. This is very important because all of this idea of bringing the computation to your laptop wouldn't be worth much if you have 8 gigabytes of memory and the query needs 10 gigabytes, and then it would just crash. DuckDB goes to great length to avoid this, so we try to be as graceful as possible in the performance degradation, and we always try to finish. Here is an example from the famous TPCH benchmark. I had the scale factor 100 dataset generated on this laptop, and I ran query 7 with the memory limit starting at 24 gigabytes and then decreasing by 2 gigabytes for every step. And what you can see is that the ideal amount of memory for this query, where it's completely in memory, is somewhere between 20 to 24 gigabytes. But if you start to run out of memory by just 1 or 2 gigabytes, it will drop a few seconds. And even if you have 1/10 of the required memory at 2 gigabytes, the query is only roughly 2.5x slower. So the degradation is really graceful, and this is well within to what the user can wait for. It's still faster than moving your data to another computer. So DuckDB is quite portable and quite fast, but it's also feature-rich. We ensure that we can read most popular formats, starting from CSV, Parquet, and JSON. We can also integrate very well with Arrow, and we use it for our integrations with Pandas, Polars, and NumPy. We can also use R, so we are not exclusive and not limited to the Python word. dplyr will work really well with DuckDB. You can even use dplyr syntax to run DuckDB queries. And we do everything with a zero-copy access, which is something allowed by Arrow. So query language-wise, we did not pick an exotic custom SQL. We actually picked PostgreSQL, which is a widely understood dialect, and we tried to cover most of it. So we have subqueries, window functions, common table expressions, all sorts of exotic joins like lateral, range, and as-of joins, as well as the pivot and unpivot, as I've shown. And one thing that's really popular among our users is our so-called friendly SQL extensions, which is basically just saving a few keystrokes when you are doing interactive analytics. So in the from first syntax that I want to show you first, what we identified is that there's a common pattern of people just firing off select star queries. And we turned this into a friendly variant. If you say from table name, DuckDB will add the select star for you, and it will return all the attributes from the table. People love this for some reason. The second is exclude columns. This is, again, a common observation that very often you have n columns, but you only want to return n-2. And of course, you can do so by spelling out all those n-2 column names, but it's so much easier to just say select everything and exclude the ones that you do not want. So exclude will allow you to do that, and it combines really nicely with the unpivot statement, as I have shown in the demo. And my personal favorite is group by all. So it is a very common mistake to say, I want to do an aggregation, and I want to group by this column, and I want to do this aggregation, but then you actually forget to specify the group by statement. And this is, of course, kind of stupid, because the computer could figure out that if you want to aggregate on the number of comments and the other attribute is the month of the creation date, then it should do the group by on that. So we added something called group by all, and this has actually been proven so popular that other vendors have now copied it. So other vendors have group by all in their system. Okay, let's take a look at the extensions on how we manage all this. So DuckDB has extensions that support reading directly from MySQL, PostgreSQL, and SQLite, as well as a number of protocols like HTTP, AWS S3, Google Cloud Storage, and so on. And these are all implemented not in core DuckDB, but as DuckDB's extensions, thanks to the powerful extension mechanism that we have. We have gone to great length at adding potential options for defining new types and functions, data formats, operators, and even new SQL syntax or a memory allocator if that floats your boat. And many of DuckDB's important features are implemented as extensions. So we have the HTTPFS extension, we have the JSON extension, and we have the Parquet extension. And these extensions work together, and they do not work in some naive way. So if you run Parquet and HTTPFS, it will not bulk download the entire Parquet file from HTTPFS and then read it with Parquet. What it will do instead is that it will use HTTP range requests to seek to the required data using the min-max indexes that are in the Parquet file. And then, because Parquet is a columnar format, it will only touch the columns that we requested. So here, if we use some stock data and we search for the ticker that says Microsoft, and then we average the price, we only touch 2 columns, and we seek into the row groups where the Microsoft stocks are. We have a spatial extension that we are very proud of. This adds PostGIS-like functionality, meaning you can define geospatial types, geospatial functions, and if you have something like the New York taxi dataset, you can load it, and within a few lines, you will be able to do something like the calculation of the aerial distance and compare it with the trip distance on how those 2 numbers differ and rank the taxi rides based on that. So the talk title said harnessing in-process analytics for data science and beyond, and I would like to focus on the and beyond bit a bit now. I said that I come from graphs and benchmarking, and this is a funny use case that I found last year. So I inherited some code base, which was written in 2015, which qualifies it as legacy code. And it was a graph algorithm benchmark where the contestants had to take a graph, like G in the top left, and they had to find connected components quickly and annotate the nodes with the number of the connected components that they are in. But the tricky thing was that we allowed them to use equivalence classes. So R1, where the left component is annotated with 1, 1, and the right is with 3, 3, 3, is just as valid as R2, where you have 55 for the left and 77 on the right. And this competition ran for a few years, and we noticed something strange. As the solutions have gotten quicker and scaled for larger graphs, the solutions could complete maybe in 2 minutes, but then we had 6 hours for the validation to complete, because the validation was written as a single-threaded piece of Java code that built 2 hash maps to find violations of these equivalences. And that was, of course, quite annoying. So what I ended up doing is that I rewrote it using DuckDB. I created an expected table, I created an actual table, and I tried to find validations of it. And I could fire off this really nice pull request, which actually reduced the code base, made the validation parallel, and made the validation a lot faster than the systems that actually solved the problem, which is the way it should be. And we didn't stop there. So I maintained this entire benchmark work suite with one of my students, and we ended up having these really satisfying pull requests when we could strip out 5,000 lines of code of old single-threaded Java code and then put in DuckDB, and it became a lot more maintainable, a lot more readable, faster, and elegant. So we really liked using DuckDB for all sorts of use cases, like generating parameters, reading input parameters from Parquet, partitioning, analyzing, and so on. And the really interesting thing is that none of these from the above are database problems. They are simply problems where you have some heavily structured data and you have to do bulky operations on them, which lends itself really nicely to SQL and the relational model. But with a regular data warehouse or analytical database system, you would never go through the hoops of setting up an actual database. But with DuckDB, because of the ease of deployment, the portability, and the sheer speed of the system, this all makes sense. So this is something that I recommend you to do next time you have to modernize a code base. Maybe there is a database problem in there, just really hidden, and DuckDB can help you out. Other places where DuckDB can help you out is simply saving costs. If you run stuff on your laptop, then you don't have to pay for an AWS instance, you don't have to pay for a license of a server, and it's likely almost as fast or even faster. We noticed that many people use DuckDB as building blocks in their applications. Maybe they have already an excellent tool chain that reads CSV, and in this case, they just grab the Parquet files, convert them to CSV, and then forget about DuckDB. This is a perfectly valid use case. And finally, we believe DuckDB is great for education because it's easy to install. It's an open, standards-compliant system, and you don't have to run a server which your students will crash over the weekend, and then you have to call your DBA, and that's just a hassle. So DuckDB helps out with that. DuckDB is not perfect. There are a few limitations, mainly around concurrency control. Because it's embedded, it didn't make sense for us to optimize for write-heavy concurrent transactional workloads. So if you have multiple DuckDB processes, you will be limited to only reading your DB file. If you want to do reads and writes, you have to restrict yourself to a single reader and writer. And continuing this thought, we also don't do distributed execution. If you want to scale, we recommend you to scale up. There are amazingly fast and powerful machines available in the cloud. You can run these machines, like a 1 terabyte machines comes at less than $10 an hour. And we recommend that you store the data in S3 and then spin up this machine, do the computation with a short burst, and likely the cost isn't too bad, and the scalability will still be reasonably good. Because we have larger than memory execution, you can scale up to a few terabytes like this. If you have tens of terabytes of data, I would say it's time to look elsewhere and find a distributed setup that will be beneficial for it. All right, so what is the DuckDB landscape at this moment? We have released version 0.9, and this year we don't plan to do any big releases. But of course, early next year, it's time for us to release version 0.10. So we will keep you waiting a bit, but then later next year, I promise V1 will be out, and that will have a stable file format that we guarantee to be backwards compatible. It will have stability and maturity improvements, as well as more performance optimizations. People often ask, what are all these organizations around DuckDB? So just a couple of sentences about that. There is DuckDB, the open source project, which is owned by the DuckDB Foundation, which is a non-profit. We have DuckDB Labs, the company where I work for, which is the company that does commercial support for DuckDB, so you can have a support contract if you use DuckDB. And there is MotherDuck, which is a venture-funded startup that creates a serverless, cloud-based version of DuckDB that does something really interesting. It takes a hybrid execution model where part of your query can run on your laptop and the other part can run on the server. And this opens up a great number of interesting use cases, from privacy to performance optimizations. So wrapping up, the reason I like DuckDB is because it feels like an old school Unix tool. So it has a state-of-the-art heart, but it's also a fully open source project that has a full-fledged CLI client. There is no enterprise version of any of that sort. We don't require you to register. You open our web pages and we don't have cookies. So it's all very old school in this regard, and it works very nicely if you're offline. You can just grab a PDF and work on the airplane with DuckDB. We also don't believe in vendor lock-in. So if you don't like DuckDB, you can take your data with a single command in one of the open formats like CSV and Parquet. So if you like this, give DuckDB a spin. Because of the portability, it's available in many places. You can go to Google Colab where it's pre-installed, and you can go to shell.duckdb.org where you can run it on your own computer in Wasm. So thanks for being here, and let's stay in touch if you like this.